Hey there, have you ever wondered if we can make our seismic data look more like well logs? In our recent study paper that's coming out in Interpretation, we introduced the Distance and Quadrant trace, so the DQ trace, a novel seismic attribute that transforms traditional wiggles into blocked sections that actually mimic porosity logs. The distance and quadrant method is pretty computationally simple and requires no prior knowledge of rock properties, wavelets, or even the basin geology. The process involves four key steps, kind of outlined here, from input data preparation using the partial near and far stack traces to approximating the AVO attributes, then using quadrant optimization through phase rotation filtering, and then finally you do the DQ trace calculation. We can see here how a conventional wiggle trace gets transformed into the DQ trace, where the gas sand response, which is highlighted in red or pink, changes from a sinusoidal wave to a clear blocked section with sharp boundaries and consistent high amplitudes. When we look at the same data in AVO crossplot space, the DQ process pushes the gas sand data points, which are the pink diamonds, kind of outward onto the circle at four specific positions. And this creates tighter clusters than the original scattered, kind of more torpedo shape of conventional seismic data shown by the pink circles. This clustering makes identifying gas sands much easier to identify and map. The way this happens is through a unique process we call quadrant optimization. So we apply phase rotation filters to the near and far stack data, which helps us optimize each sample point in the seismic data, so not just the peaks and the troughs. This is fundamentally different from traditional AVO attributes, which often lose information at those zero crossings. Okay, so this is where it gets interesting. The DQ trace has a direct mathematical relationship with acoustic impedance and VP-VS ratio, which explains why it correlates so well with porosity. So when we tested it out across all four AVO classes using synthetic data, we found not only that it differentiates the gas sands from the wet sands, but it also enhances the fluid contacts, as you can see here, kind of maintaining the accuracy across different bed thicknesses. One of the more powerful aspects is its histogram analysis capability. So unlike traditional seismic data, where the shale responses kind of overwhelm the histogram, the DQ trace pushes the gas sand responses to the edge of the distribution, making them much easier to identify and map. If you want to learn more about how to implement the DQ trace in your workflow, you could check out our detailed methodology and recommendations for different geologic settings in our paper, or you could always reach out to me. We have all of this information and more on our website. Thank you for watching the video, and I'll see you next time.